Now, to look at mechanical physiology, we're talking about the processes where the blood fills up the cardiac chambers and it gets pumped out of them. And when your cardiac muscle cells contract as a unit, they have one coordinated contraction. They're not all contracting at different times. It's coordinated. It's your heartbeat. And when your heart beats, the cells are arranged in a spiral pattern, so it's more of a ringing action, like you're wringing out a cloth when the heart contracts. And there are pressure changes that happen that drive the blood flow through the heart. And the valves keep it from flowing backwards. So all the events that take place with one heartbeat to the next, that's called the cardiac cycle. Your blood flows because of pressure gradients. When the ventricles contract and relax, the pressures in those chambers changes, and so it causes the blood to push on the valves and either open them or close them. When the ventricles contract, the pressure rises above the pressure that's in the atria and in the pulmonary trunk and aorta. So you got high pressure in the ventricles when the ventricles contract, and that causes the blood to pump out of the ventricles into the vessels, and that causes the valves to change. When the ventricles contract, it shuts the AV valves and it pushes the semilunar valves open so that the blood can exit the ventricles. So you can see that here. You've got the ventricle is full of blood, and when it contracts, those papillary muscles pull on the chordae tendineae and they shut the AV valves, and the force pushes the blood up through the semilunar valve and opens it up. When the ventricles relax, the pressure in the ventricles falls below what it is in the atria and in the pulmonary trunk and the aorta. And that opens back up the AV valves so the blood can drain from the atria into the ventricle. And then the higher pressure in the pulmonary trunk and the aorta, that pushes the semilunar valves closed. So you can see here, the ventricles have pumped the blood out. So now the pressure is higher up in the aorta and the pulmonary trunk, and because of gravity, the blood flows down a little bit, and that closes the semilunar valves. At the same time, the atrioventricular AV valves open because the papillary muscles have relaxed and it's now open again. Under normal conditions, you don't have really loud noise from the blood flow as the AV valve closes and the semilunar valves close. Or as they're, let me back up. Normally, when blood goes through the open valves, you don't hear anything, but you hear sounds when those valves close. So the sounds are the vibrations of the ventricular and the blood vessel walls. And the sounds are lub or S1, that's when the AV valves close, and S2 is dub, so it's lub dub, and that's when the semilunar valves close. And the S1, when the AV valve closes, it's louder and longer than the S2 when the semilunar valves close. The cardiac cycle, you have a period of relaxation and a period of contraction. Relaxation is called diastole, contraction is systole. So you've got atrial diastole occurring when ventricular systole occurs, and you've got atrial systole occurring when ventricular diastole occurs. And that's because of the AV node delay, the way it's slower than the SA node. So both sides of the heart are working at the same time to pump blood into their respective circuits. The right side is pumping it to the pulmonary circuit, the left side to the systemic circuit, but we divide the cycle into 4 main phases, and it's all based on what's going on in the ventricles and how the valves are positioned. So we've got filling, contraction, ejection, and relaxation. Now, a little side note here, when they listen to your heartbeat, sometimes they hear a heart murmur, and that's when you've got very turbulent blood flow through the heart because of defective valves. And it could be the chordae tendineae that have problems, or you could have holes in the inner atrial septum or the interventricular septum. Sometimes a child will have a heart murmur that really is not a defect. The S3 sometimes is heard, and that's just before the blood starts to flow in the ventricles, right after the S2. And if an S4 is heard, it's after the blood has left the atria and gone into the ventricles, and it happens right before S1. And sometimes that's because the ventricle is enlarged. They both represent pathology or disease, but sometimes it can be heard in a healthy heart, just not all the time. Now, looking at the cardiac cycle in these 4 phases, the ventricular filling phase, that's when the blood's draining from the atria into the ventricles. So you've got low pressure in your ventricles. And you've got higher pressure in the atria, the pulmonary trunk, and the aorta at this time. That closes the semilunar valves because the pulmonary trunk has high pressure, the aorta has high pressure. That closes those semilunar valves. So we're not going to have any backflow going into the pulmonary trunk and aorta. The atrioventricular, the tricuspid and the mitral valves, are open because of that high atrial pressure. And blood flows down the pressure gradient from the high atrial pressure into the ventricles where there's lower pressure. And 80% of the blood that's in the atria will drain passively because you've also got gravity on your side here. That's the ventricular filling phase. So initially the atria are in diastole, and the blood just continues draining into the ventricles, and the pressure gradient gets slower and smaller, and then atrial systole happens, and the atria contract, and they eject the remaining 20% of blood volume. And at the end of systole in the atria, the ventricle has about 120 milliliters of blood, and we call that end diastolic volume because it's the volume of blood that's in the ventricle at the end of ventricular diastole. The ventricle's relaxed, the atria's put all this blood in there, and so at the end of the relaxation of the ventricles, we have end diastolic volume, which is 120 milliliters. Then we start ventricular systole, and this is very quick, and we call the very beginning of this the isovolumetric contraction. Okay, the pressure in the ventricle is going to rise because the ventricles are starting to contract. That opens the AV valve, closes the AV valve and makes the first heart sound, that lub. But the pressure in the ventricles is not high enough yet to push open the semilunar valves. So you've got both the AV valve and the semilunar valves, they're all closed. So the volume of blood that's in the ventricle doesn't change. So it's iso, which means equal volumetric contraction. The same as the end diastolic volume of 120 milliliters. All of the valves are closed, so we've got isovolumetric contraction at the beginning of ventricular systole. Then we go to the ventricular ejection phase. The pressure in that ventricle gets so high, a lot higher than you've got in your pulmonary trunk and your aorta, That pushes the semilunar valves open so the blood ejects through from the ventricles. And so the pressure in the pulmonary trunk from the blood in the right atrium and in the aorta from the blood in the left atrium rises, and it gets to the point that's as high as it is in the ventricles. And that's going to slow the ejection of the blood down. So we are going to eject about 70 milliliters of blood during this ejection phase. That means we're going to be left with 50 milliliters, because remember, we were 120 milliliters. We eject 70. I'm sorry. I have to sneeze. Apologize. Sorry. Goodness. And when we eject it, we're left with 50 still in the ventricle. That's in systolic volume. Then we go to isovolumetric relaxation. Very briefly, this is when ventricular diastole starts and the pressure in the ventricles is declining. That shuts the semilunar valve. That's when we hear S2, or the dub. The pressure in the ventricles is a little higher than in the atria, so the AV valves are still closed. So blood is not going anywhere. It's constant. That's why it's ISO, the same. Isovolumetric relaxation. We can see these here. This is the filling. You've got the blood that's going into, it's in the atria, and it's flowing through into the ventricles. The ventricles are relaxed. The tricuspid and the bicuspid are open, and the atria will contract, atrial systole. The semilunar valves are closed. And then we get to ventricular systole. Now, we have end diastolic volume. We put all the blood here in the ventricles. Okay, it's going to be around 120. So the ventricles start to contract here. The pressure builds, but it's not high enough yet for the semilunar valves to open. And also, because systole in the ventricles has started, we've closed these AV valves. So now the pressure's going to rise enough that the blood will push open those semilunar valves, and the AV valves are still going to be closed. They're still closed. The atria are in diastole. They're relaxing. That pressure opens those semilunar valves, and the blood is ejected from the pulmonary trunk to the pulmonary arteries, and from the aorta to all the arteries in the body. All right, then we get to isovolumetric relaxation. We've pumped out about 70 milliliters, so we're left with about 50 milliliters, which is in diastolic volume. The AV valves closed. The pressure's low enough here in the ventricles that the semilunar valves are closed. And this is when the atria is still in diastole. They're filling up, but all the valves are closed. And then it starts over.